Okay, so question 3, reaction schemes or reactions. So we knew this, look, it's typical questions to have. We know that we're going to be asked to draw or to work out what reactions are happening, and this is an example here. So here they've got a flow diagram instead of a bigger two-dimensional reaction scheme. And we're starting here with an alkene turning to an alcohol, going to a haloalkane, and onto an alkene again. So first question is, use the reaction scheme above to complete the following table. The formula of each reagent, including any necessary conditions, the type of reactions. Okay, reagent A, we're going from a alkene to an alcohol. So here it's an addition reaction. Let's write that down. Addition. And in this case we're adding water, but of course, right, though we are adding water, we just can't have this happen by adding water. It's got to be in acidic conditions. Now you can just put H2O / H plus, or sometimes H2O / H2SO4. They'll both be acceptable. Second change we see, we've got a hydroxy or alcohol functional group turning into a chloro or a chlorine functional group. So we've got a substitution reaction here because we're replacing one with the other. Substitution. And in this case, yeah, I have a couple choices here. I'm just going to put SOCl2. Okay, I could use PCl3 or PCl5. They will be fine and will be acceptable here. The last one, we've got turning into an alkene. We're removing a hydrogen and a chlorine. This is an elimination. Okay. And in this case, in order to eliminate, this is maybe one of the more difficult ones to remember, we're using hydroxide. In this case, I'm just going to write down potassium hydroxide. You could write hydroxide or, OH minus. But the most important part here, if it's going to an alcohol, this case it's going to an alkene, so the hydroxide must be dissolved in alcohol. That's ALC to get our elimination reaction to happen. If we didn't do that, then our major product would be an alcohol if it was dissolved in water. Okay, so let's move this up a bit. And here we've got the following reaction C happening again, and they're saying, is this a major or minor product? Okay, so in this case we're trying to remember the rule about what happens when we eliminate a chlorine and a hydrogen. So this is the opposite to Markovnikov's rule, where the rich get richer. This is the rule that the poor get poorer. Poor get poorer. Okay, so when we mean the poor get poorer, what we're looking at is the carbon atom that the other end of the double bond could possibly join to. And we've got two choices. We've got the one on the left here, okay, or the one on the right. The one on the left is poor, okay, this one here is poor, because it only has 2 carbons, and this one is rich. So what's happened is the poor one is going to get poorer, or it's going to lose its hydrogen for the majority of the reactions that take place. Okay, so let's say that we've got 1,000 of these reactions taking place. The majority of the time, the molecules will lose the hydrogen that is the poorer one. And so this one here is following the rule, the poor get poorer. So this is the major product, because the poor one got poorer. And we can say the carbon that had, we could say the poor get poorer, but let's be more specific here. We can say that the carbon that had the least, now let's say the poor get poorer. the pore get poorer. That is, the hydrogen is removed. Hydrogen atom is removed from the carbon with the least hydrogens the majority of the time. Okay, last page. Looks like another reactions question, so let's have a careful read of this. Butan-1-ol can react separately with PCl5, acidified dichromate, and concentrated sulfuric acid. Elaborate, which means expand or to give more detail on these reactions, or the reactions of this with each of the three reagents. So the detail they want us to give is bullet pointed here. The type of reaction, okay, and reason why so make sure you put the reason. If you don't put the reason, you're not going to show comprehensive understanding. The name of the functional group formed in each product, and the structural formula. Okay, for structural formula, we're going to have to draw a reaction here, I would say. So let's do butan-1-ol for a start with PCl5. I like drawing the reaction, getting that out drawn first. It sort of helps me understand what's happening. So what is it? Butan-1-ol PCl5. Let's draw that. So I'll draw out the structure. Butanol, butan-1-ol, PCl5. Now no, look, I can see the OH here. I can see that here is a molecule that has lots of chlorines attached to it. I've seen this one before. I know what's going to happen. It's going to produce the organic product here. Now, that is a bit more room here. Cl, there we go. Now, we know that there are other inorganic products that are in this reaction, but I'm not concerned about writing those down for this. And the reason is it hasn't asked for the complete equation. The last bullet point has only asked us to structural formula of the organic product, and there it is. Okay, so we've got whoa. Let's check this one again. Okay, easy mistake here. So I got carried away talking. 1, 2, 3, 4, 5. 5 carbons. That's not cool. Let me just put the hydrogen in there. Right? Look, just cross it out. It's a mistake. Let the examiner know it's a mistake and just put it in the hydrogen. There we are. We've got the correct answer. Have I named the functional group? It's no, I haven't. So let's write it underneath. It's a haloalkane. Could have written the chlorofunctional group, but that's fine. Type of reaction. Okay, let's write this one just above here, and obviously this is a substitution. I'm going to have to say why it is a substitution. This is a substitution reaction because the chlorine has replaced the OH functional group. Substitution. As the cell has replaced the OH functional group. Cool. Fantastic. Okay, so butanol again, and organic product. So let's draw the next one. In this case, I'm pretty sure it's, pretty sure, I mean I know it's oxidation, and practiced enough of them that we'll be expecting an oxidation equation at some stage in the examination paper. So here it is. So 1, 2, 3, 4 again. Well, I most really didn't have to write out the whole thing again, but it means I'm less likely to make a mistake. As you saw in that last one, really easy just to make a wee fundamental mistake by like putting one too many carbons. So when I put out my working or my whole equation there, I can look back and check that I'm actually not doing anything or haven't done anything silly that I'm going to lose my valuable marks. This one here, now we know that it goes to carboxylic acid. There is an aldehyde intermediate. At this stage, because they haven't asked anything specifically about an intermediate, or they've just said that they have that reagent, we're going to expect that it goes to completion. CO2O7 2 minus H plus. Okay, again, this is a carboxylic acid functional group. And this is oxidation. Well, that's a bit messy. Right, I think I'm missing something here, and that is the type of reaction and the reason why it's classified as that type. Okay, so why is this oxidation? So we could say that the definition of oxidation is that the organic product here has gained an extra oxygen or oxygen bonds. So we could say that the oxidation number of the carbon that the oxygens are attached to has increased, or we could draw a half equation here and say that it's lost electrons. I'm just going to go with the organic reactant has gained oxygens. Yeah. So it is oxidized. Let's say oxygen bonds. Okay, so it is oxidized. Look, I'm a bit worried that the examiner's going to think I don't know what oxidation is. If I do, I might leave a wee bit of gap here. I'll come back and write an oxidation half equation for this, just so that they know. I'll go on to the next one, and I'll just have a think about whether I need to do that, how much time I've got. Okay, sulfuric acid, alcohol. Sounds like elimination to me. Let's draw this last one here. Last question of the paper. And there we go. Concentrated H2SO4. H2SO4, right, and we're going to elimination. Obviously the double bond is going to form adjacent to where I took the OH off. Put my hydrogens in. And this is obviously going to be an alkene. And it's elimination because alkene, elimination. Okay, so this one, really simple, both the OH functional group and an adjacent or a hydrogen on N adjacent. Carbon were removed and a double bond was formed. Elimination. Okay, that was nice. Okay, so we finished off the paper with kind of lots of writing and a few equations. I said I might have gone back and said why this was oxidation, given an oxidation reduction half equation on one oxidation half equation. Look, I'm pretty confident that I don't need to here. So it has, it's gained oxygen bonds. Okay, that's pretty good. That's pretty clear for them. Have I done everything that they've asked? Type of reaction, substitution, oxidation, elimination. Yes. Reason. Yes, I've got a reason for each. Functional group, haloalkane, carboxylic acid, alkene. Yep, done. Structural formula of the organic product. Yes, I have that for each. So everything's covered here. I'm looking pretty good to get a comprehensive understanding for this question. Okay, so that's me. I've gone through and answered the questions in this paper. I hope that my approach and what I've done helps you out.